this floor is quiet for an hour. So let's start. It's my great pleasure to introduce Dr. Ben Horowitz from IPMU. So I think not just for cosmologists, but it will be a great dream come true if you can, just by observing galaxies and being able to see the dark matter distribution. And furthermore, it will be even better if you can rewind the clock and see how these cosmic structures come into place. And this is the topic that, one of the topics that Ben has been working on. This is called field level inference. So Ben got his PhD from Berkeley under Seljak in 2019. And then he went to Princeton as a postdoc fellow. And then after a brief stint back to Berkeley lab, he's now a Catholic IPMU fellow at the Institute for the Physics and Mathematics of the Universe, a post that Inference held before. And so, as I mentioned, Ben is an expert in field level inference, and to achieve this goal, he has made pioneer efforts in making things differential, like for HOD models, differentiable, and then recently he also made hydrodynamical simulations differentiable. That allows him to use Hamiltonian MC processes to really make this density reconstruction possible. So let's hear all about this. Let's welcome Ben.
Thank you so much for the lovely introduction. It's great to be back in Taiwan and to be able to share some of my work and kind of the vision for the future and where I want to take this idea of field level inference to in the coming years. So a lot of my work thus far has been motivated by this kind of twin development. So the past 5-10 years, we have a wealth of data, a wealth of multi-wavelength data from kind of ongoing surveys like PFS, which I'll talk about in this talk, from the glossy images that JWST and HST are producing. So we have this development on one side, and then on the other side we have developments of simulations where people are really diving into smaller and smaller scales, trying to reconstruct across a wave of physical sizes from large cosmic structures down to individual stars and supernova remnants. So the question is, how do we really connect this development from simulations to these developments from the observational side? And so what I hope to convince people of in this talk is that there's kind of a cool way forward with field level inference, with explicitly using kind of the techniques that have been developed in the machine learning community, so using GPU acceleration, using high dimensional optimization and high dimensional sampling techniques to apply it to this to these astrophysical problems and really have a data-driven model and a data-driven framework to understand the physics that we're observing in the universe. So most of my work in this kind of field has been motivated by galaxy formation and galaxy evolution. And so people have probably seen variants of these kinds of videos before, where we have the joint evolution within some simulation framework, the stellar lights. So these are stars that are forming and making nice, beautiful galaxies with the underlying gas distribution in the cosmic web. And the interplay between the gas and the filaments and the feedback processes in the galaxies is one of the main kind of goals going forward in astrophysics, and a key thing we need to understand with next generation surveys. So we can kind of see here this beautiful, the galaxies forming and creating this beautiful feedback processes as stars form and injects gas into the intracluster medium and maybe outwards to the intergalactic medium. And so the hope is to understand these kinds of processes, not just from the standpoint of doing forward simulations, but actually connecting those directly to observations. So towards this kind of goal, we have a few different focuses. So from the observational side, I've been working a lot on the Prime Focus Spectrograph, which I know a lot of people in the audience are familiar with. I'll kind of give an overview of what PFS is and what we're hoping to do with it, how we're hoping to both study the galaxies and the gas across cosmic time. I'll be talking about how we're going to use field level inference to approach this topic, how to reconstruct the underlying gas distribution, and also reconstruct the formation history. And then finally, kind of what I'm most excited about nowadays is pushing to smaller scales and more detailed modeling using differentiable hydrodynamics to actually be able to put in these kind of subgrid physics prescriptions, putting in star formation into the simulations, but then be able to actually optimize for it to figure out what is the real physics driving the universe as we observe it today. So from the PFS standpoint, PFS is the Prime Focus Spectrograph is an instrument being deployed on the Subaru telescope in Hawaii. Its kind of distinctions are that it has a very wide field of view as well as broad spectral coverage. So it's very useful for a lot of different science. So people are studying stellar populations, do galactic archaeology. People are studying wide field kind of cosmology, doing deep observations for cosmological analysis. And then what I'll talk about next is the galaxy evolution side. And it's part of this larger strategic science program with HSC, with the hypersuprime cam. And so there's a lot of synergies that can happen by combining the photometry of HSC, obviously we're using it for the targeting, with the spectroscopy of PFS. So for the galaxy evolution in particular, the kind of goal is to reconstruct cosmic evolution, reconstruct galaxy evolution over cosmic time. So at high redshift, we're targeting these line alpha emitters, these kind of narrowband filters. This is the part I know the least about, so hopefully you don't have any hard questions about that. We have this intermediate redshift regime of IGM tomography. I used to call this high redshift, but people started laughing at me. Redshift 2 is no longer considered high redshift. Okay. And so here we're going to be using absorption line studies to map the 3D cosmic web. And then at low redshift, which I guess means redshift 1, we're doing a kind of more traditional galaxy survey where we're targeting lots of galaxies to try and reconstruct the cosmic web with the galaxy density. And we're doing this galaxy evolution survey across 4 different fields, each with multiple pointings. And the kind of design of this is to really enable this kind of synergistic reconstruction where we can really have lots and lots of wavelengths that we're observing and that we can combine together to try to reach real interesting physical constraints on the galaxy formation and the galaxy evolution. So already we're taking data. So far we have 1 field here complete from just this past year, and we're slowly taking data in some of these other fields for galaxy evolution. But the particular aspect I work on the most is this idea of how to connect together large-scale structure. So I lead the large-scale structure component of galaxy evolution, kind of interestingly between the cosmology on one side and the kind of more focused single object studies on the other side. And one of the main probes I look at is Lyman alpha forest. So people are probably familiar with this, but the idea is that if you have a low redshift source, which has continuum emission, you get this continuum feature. And if you're at low redshift, you don't see many absorption lines. But if you're at high redshift, you do see all these absorption lines. And these absorption lines correspond to the neutral hydrogen density along the line of sight. So there's a classic video I have. Maybe I need to press the button. To show kind of what this means physically, you have some high redshift quasar, the light's passing through on its way to us. As the light passes, you get this redshift of the spectrum, and then you have, as it passes through the actual filamentary structures, these are the things we're trying to study, you get these absorption features. And these absorption depths correspond to the amount of neutral hydrogen there. So this gives you essentially a one-dimensional picture of the neutral hydrogen. And so the idea is that we want to make a 3D map out of this. So how do we do that? Well, you can imagine if we have some underlying density. So this is from a hydrodynamical simulation of the neutral hydrogen. In this case, we're showing it as the flux. So 1 means complete absorption. Sorry, 1 means no absorption. 0 means complete absorption. We can take a grid of sightlines. So if the universe is so fortunate as to give us a little row of galaxies or a row of quasars, we can then actually take this data from each one of these line of sight, look at the actual, what we actually observe is this absorption features from the line alpha forest. And you can almost by hand draw connecting the dots, right? You can connect these. See there's some really large, coherent, large-scale structure here. Over here there's a void. Over here there's maybe some kind of filaments. And the idea is that if we're able to connect these lines together, build this three-dimensional map, that gives us a good idea of what the large-scale structure is in this environment. And so rather than having to take maybe thousands of galaxy spectra to pin down each single point, one single spectra of one of these high redshift sources gives you a whole one-dimensional view. And if we make the further leap that this neutral hydrogen, this absorption, is proportional to the dark matter, you also just have a map of the underlying dark matter field. And so this kind of relationship, this assumption, a lot of work, or we'll pick it apart later on in the talk, dark matter, or neutral hydrogen absorption equals dark matter, is known as the fluctuating Gunn-Peterson approximation. That basically this optical depth that's creating this flux is proportional to the dark matter to some power. And so this is the fluctuating Gunn-Peterson approximation that underlines a lot of these studies. But we kind of know from hydrodynamical simulations, so here's this illustrious simulation from earlier, that there is deviation from this idea that there's a one-to-one correspondence. So here is the dark matter density versus the flux over density. So this is just dividing out by the mean flux. If you look at the fluctuating Gunn-Peterson line here, there's this deviation when you look at hydrodynamical simulations. It's not just a one-to-one relationship between neutral hydrogen density and dark matter density. And as we kind of saw from the earlier animation, there's a lot of complex physics going on. You have stars forming, you have galaxies forming, you have sources of inflow and outflow from these galaxies, all of which will change this equation of states, and all of which are a sign of these kind of feedback processes going on. And if you look at different hydrodynamical simulations that have different feedback prescriptions, you get different deviations from the fluctuating Gunn-Peterson approximation. And so if we're able to trace this flux field, if we're able to trace the neutral hydrogen density, and we're also able to trace the dark matter density, we can do this comparison and actually pick apart what is driving feedback processes. What environments are dominated by feedback, what environments aren't, and how does that relate to the underlying physics. So we've been embarking already on these kinds of tomographic surveys, even before PFS was underway. So over the past now almost 10 years, we've been working on this Clamato survey, which I led the second data release of. And so the Clamato survey is a much smaller field. So if you remember PFS, each pointing is roughly 1 square degree. Here we spent a while on Keck, and we collected 0.25 square degrees. So every single pointing of PFS is 4 times what you'll see here. But even so, from these 320 background sources where we're able to see neutral hydrogen absorption, where we're able to see this line-alpha forest, we can already build up this three-dimensional map of the underlying flux. So already from this map, you can see large voids, these big protoclusters. One of these is called the Hyperion cluster. People have heard of that one before. It's, I think, one of the highest redshift protoclusters, at least known to date as of a few years ago, as well as these really large cosmic voids. And so we can already start to trace out cosmic structure at high redshift and use these properties to relate galaxy properties with their environment. So now the question is, how do we tie this together to the simulations, right? In these examples, we have, this 3D map of flux, but what does that mean in terms of the simulations? Can we run a simulation that actually reproduces this specific observed flux field? And this goes to this idea of reconstruction or field level inference. Some people call it explicit field level inference, dynamical reconstruction. There's quite a lot of names thrown out that all are more or less overlapping. But the idea comes down to this. we have some underlying density field that we want to reconstruct. So just here I made a toy little example in 3D of a dark matter density field. This was made with a particle mesh code. People who haven't used these things before, it's very, very fast to generate fake universes. You basically can, particularly if you do this all on GPU, it takes maybe 5 seconds or so to generate 128 cubed volume this way. So we have this beautiful map. You can see the filaments, we can see the voids. And so let's imagine that we actually directly observe this dark matter field. And now we want to run a simulation that matches this underlying field. So you can just choose a random initial condition. Usually in cosmology, we talk about generating Gaussian random fields, these initial fluctuations from the Big Bang. And so we'll be taking these fields, we're going to be evolving them with dark matter. And let's see if this particular realization of a Gaussian random field corresponds to this observed field. So we can run it forward. Should be an animation. Okay, well, hopefully my other animations work. So you can run this thing forward, and you can see, does it match this field match this field? Not really, right? There's this really large residual that's present when we subtract these fields. As you would expect, right? If you're just taking a random field, another random field, no reason that they could match. You can do this again. You can have another example here. And again, you could look at the residual, and they also don't match. Again, not very surprising, right? You can just keep on doing this. It would take you probably much longer than my talk, much longer than maybe the age of the universe, to just randomly take draws and get them to match. So what is the solution here? The solution here is to use derivative information, gradient information, to inform how we update the initial guess. You're not just choosing random fields, you're making informed updates. And so the way that works is we can imagine we have a pipeline where we have some initial parameters, we're generating some initial field, you evolve the field forward in a normal forward simulation, and at the end we map to some observable field. So this is kind of the generic forward modeling framework, what everybody does who makes simulations to try and match their observables. And now we're going to go one step further though, and try and turn this into a differentiable framework. So at the end we have this observable field, and we're not just going to take it in isolation, we're going to make a likelihood comparison to some data. And so in this talk I'll be showing both examples. This is real data as well as just simulated data to prove the framework. We have some likelihood here. And if we were able to set this up in a differentiable framework, you can backpropagate through. Backpropagate the whole simulation and get the derivative of this likelihood with respect to your initial parameters. And so what this tells you is, how do we have to move these initial parameters to best minimize the loss or best maximize the likelihood? And so this approach is very analogous to what people do if you've ever trained a neural network or done things like that, where we're really trying to figure out how to use the physical model to inform the updates to our system. So there's been quite a little bit of an industry developed for making these kinds of differentiable models for dark matter. This is one of the most kind of well-studied versions of this. It goes back almost more than 10 years now to the Borg collaboration, the Elucid collaboration, where they were doing this type of approach for reconstructing the nearby universe from SDSS galaxies. In those cases, to do this gradient propagation, they actually hand wrote down the actual gradients because they were doing things in a perturbative framework. It was pretty easy just to write down the equations for what the gradient of your likelihood should be from your initial conditions. But nowadays there's been a lot of development in machine learning, and there's a lot more money poured into machine learning research than there is into astrophysical research, like it or not. And so we can actually, though, take advantage of that and use a lot of these machine learning frameworks, things like TensorFlow, PyTorch, JAX, and code up our frameworks using those tools and take advantage of their automatic differentiation. So you don't have to hand write down the gradient of every single step in your simulation. Basically, if you can forward model it using these frameworks, if you can write down your code in JAX, there's a pretty good chance you can backpropagate through it. There are some subtleties to that in terms of how you set up your simulations. That's kind of the leading order effect. Wait, question?
Sorry, what does adjoint mean?
Oh yeah, so here you can see, so the adjoint method is kind of a fancier way of doing autodiff. So autodiff is kind of, it's not quite the naive chain ruling back through this, but it's kind of analogous to the chain rule. With adjoint, it is actually you are solving the equation, the adjoint of the equations. So basically you are, in some ways, kind of backwards solving your system. And that has a few advantages because you don't have to save as many of these intermediate steps. So when you're actually doing this back propagation, you have to either save or recompute some of these intermediate steps along your simulation, which could have very large memory impacts. But if you instead are kind of doing it all on the fly in this adjoint way, it ends up being cheaper from a memory perspective. And
Question.
okay.
Yeah, for the case of neural network training.
Mm-hmm.
So from my experience, so we have some limitation due to some statistical stochasticity limitation of the sampling. For the case of this differential approach, can you avoid this kind of unwanted stochasticity in the training?
Unwanted stochasticity in training. So you're talking about like in terms of how you update the parameters?
Or
what?
likelihood estimation.
Like this. Yeah, like I think for a large part, because of these are physical models and you're solving differential equations, the new kind of numerics of it are controlled by however you would otherwise be modeling the differential equations. And so that ends up being kind of like your numerical error is constrained by that, which I think is a little bit different than, for example, training neural networks, where when you have all these nested layers, you can kind of get like floating points, precision type issues, which could more likely dominate it. I don't know if you're talking about the floating point error stochasticity. But for the most part, like it is true that depending on how you initialize your system, you can get very different solutions. So like for most examples I'm showing in this talk will be optimizations. So you're just choosing kind of random starting point, evolve, not evolve, but optimize to find the best fit. But it's true that best fit point could depend on the starting position. And so in practice, what you would do for a lot of end analyses, and I'll show a couple examples of this, is you run HMC, so Hamiltonian Monte Carlo, where you can actually better explore this space.
Sorry, can you go back one slide?
One slide.
So for this, U0 to U1 to U2, etc. Are you evolving in redshift, or you are finding different initial conditions?
So this is like evolving in redshift. This is like running your simulation forward in time. So these are like different time slices as you go forward. So like if you're doing the examples here, I'm just showing like one redshift box, like the redshift 0 box. You could imagine changing this around such that you're saving slices for a light cone, or if you're evolving a different kind of system, you're not starting from cosmological initial conditions, you could do something, you could set up your time differently. But this is basically just meant to be whatever slices of your simulation or time steps of your simulation. Okay, cool. So I think I'm going to play around this a bit because I think my animations are all a bit broken, and I think it might be due to this way I'm advancing the slides. Just double check this. See how it works. So, anyway, so what we're going to do here is we're going to use differential methods to try and optimize our likelihood. So we're not going to be stuck guessing random initial conditions and seeing if they work. So the idea is we're going to write down a loss for our function for our system. This here we're just going to use a mean squared error type loss. You can imagine, depending on what probe you're using, you might have a different likelihood you want to use. We're going to take the gradient of this loss, respect to our initial field, which I'm just calling S here. And so in the end, you have this term kind of comes out by chain rule. And so this is this differentiable simulation. So here you can actually look at the derivative field. It's fairly easy to calculate within this particle mesh simulation. And you can basically figure out how you should update your initial guess of the field based on this calculation. So So something is definitely broken a bit with my animations here. Let's see. Okay, cool, so that's working. So yeah, so here we're gonna go through this process. We're iterating through. Each time we evolve our field forward, we look at the residual field, and you can see that we're updating our initial condition here. And each time we're slowly reducing the residual, and now we don't have to wait the age of the universe to guess the right field. We can actually quickly find and optimize for a fairly good solution to match our observed data here. And in the end, in this case, it kind of converges visually within 10 or 14 iterations. So doing this kind of optimization, even in full 3D, ends up being maybe a minute or two on my laptop. And so to make this a real rigorous Bayesian analysis, we want to include a prior, right? Our posterior is the sum of a prior term and a likelihood term. For a lot of these cosmological analyses, we're going to be talking about it in terms of the initial phases. So these are basically essentially where we're putting the fluctuations. And we can also extend this and not just look at optimizations in terms of the phases. We can also add in cosmological parameters and astrophysical parameters. And so there's been a bit of work on this within this dark matter framework to try and do cosmological analysis with these types of approaches. So we aren't really restricted to what distribution you choose. You can choose any distribution you want. So here is an example where I just loaded up the map of Taiwan. I optimized, again, it only took maybe 10 minutes. I didn't have to burn too much GPU time to figure out initial conditions that evolve such that the projection looks like your favorite island nation. So there's, of course, a lot of choices we can build up here. So there's, the way I kind of think about it is there's basically a tinker toy set. You can kind of put together your tinker toys or put together your Lego bricks however you want to set up the analysis you want. And the most commonly done analysis thus far has been these galaxy bias analyses. So you take your dark matter field and you apply a bias model. So you can either do like an Eulerian bias, just multiply the dark matter field by some constant and say that's your galaxy field. You can do EFT type things if you're so bold. So that's the galaxy bias, and we'll explore it. And then we can do line alpha forest, which I'll show here in a second, applying the same techniques to make three-dimensional maps from the line alpha forest data. You could look at other techniques or other observables like 21 centimeter, and then going forward, I'm very excited about going beyond these kinds of bias models and actually doing full hydrodynamics, which I'll talk about later on in the talk. And you can also extend this other trick to combinations of tracers. This is where I think a lot of the benefits of these kinds of field level approaches really, where the synergies really come out, because you have the pixel correlations, you have some map of something, and you have a map of the line alpha forest, you have the map of the galaxies. Each one is telling you different things about the evolution. But because you're evolving the same volume forward, those correlations will come out from the dynamics. And so we'll see that later in the talk as well. So the particular reconstruction scheme that I developed, I call TARDIS. And so like before, we're taking our initial density field, we're evolving it forward to a final density field. We also keep around the velocity field, which we'll use to perform redshift space distortion. So we'll apply the Fletchering and Peterson approximation to get our real space optical depth. And then we'll use the velocity field to redshift space distort it to get our actual observed flux fields. We can read it out the actual positions of the data and create a likelihood term for the data. And then we can use gradient descent to optimize to find our initial conditions. So here's an example inspired by the Prime Focus Spectrograph, where we have our initial density field, our final density field. We have a few example lines of sight. It's just cartoons of the lines of sight. And we're iteratively trying to figure out the initial density field, predicted redshift 2 density field, and here's what we're actually doing the reconstruction on. So we're actually trying to match the observed spectra of our observables. Is that a hand back there? Yes.
Are the solutions unique?
The solutions are not unique. Yeah. So this goes back to this idea that you might want to end up sampling these in abstract. But it turns out for just the purpose, let's say if your goal in the end is just to have the best fitting flux field or something like that, or the best fitting field. Even if you start at different points, you might have slightly different initial conditions, but they actually will all evolve to a very similar late time field for this problem. But for more complicated physics, you might get a different solution. So here you can kind of see an example.
Sorry.
Oh.
So can you go back?
Okay.
Suppose your goal is to match the redshift 2 density field, and you said a bunch of initial conditions can all evolve into that. But there's no guarantee that if you further evolve these simulations to redshift 0, they will have different density distribution.
Yeah, they could have slightly different density distributions. Yeah, like we did some tests where we would further evolve to redshift 0. So one of the kind of, I don't think I have a slide about this, but one of the kind of key science questions we were asking when we were starting this process is try to make a rigorous definition of a proto-cluster. So a lot of people look at redshift 2, they find these kind of overdensities, and this kind of question, is this a proto-cluster? Is this actually going to collapse at redshift 0 to be a massive cluster, maybe something like our own local group type of cluster? And so we did some analyses where we would run this forward, we would run it to redshift 2 to do this kind of likely comparison, but then we would keep on running it to redshift 0, pick out halos there, and run it back. And we were finding that we were able to really accurately pick out the protoclusters, even from that one realization. So we were actually getting very similar redshift 0 halo fields from this reconstruction. So I think it's not necessarily super robust. It's like, I'm sure there's some slight variation at redshift 0, but at least the level of the statistics we were looking at, it seemed like it was giving a good redshift 0 result. So if your goal in the end is just to make a pretty redshift 2 flux field, you just want to know where the neutral hydrogen is at redshift 2, this method outperforms the Wiener filter, which is the method that we used before for Clamato, that earlier map. It's in the end kind of equivalent to having something like 50 to 75 more sightlines. And where that comes from is because you have the added assumption that the structures we're seeing comes from gravitational evolution, which I think is a fairly reasonable assumption to make. And this type of technique builds that into the actual inference pipeline. So we can do this on this Clamato field from earlier. We can actually get our initial conditions in the real universe. So here was the what we think of the initial conditions in the Clamato field. You can see outside of where we have data, you kind of have this decaying mode away, which is kind of Wiener filter-like. But these kind of exterior modes are important because they, of course, still inform the gravitational evolution within the volume. You want to keep you want to make sure you reconstruct your large wavelength modes and evolve them consistently, because otherwise it might mess up the dynamics inside your volume. And so here's a simulation. This is the output of the TARDIS reconstruction, showing the reconstructed cosmic web that TARDIS reconstructs in the Clamato field. So you can see that, again, these large voids, you have these yellow things that we identify as filaments, and we have our nodes, otherwise known as galaxy clusters. We can go even a step further and say, well, why don't we throw in our initial conditions to a normal hydrodynamical simulation code and see, can we perform a similar kind of reconstruction? So although the Arepo code and the TNG galaxy formation model, these are not yet differentiable, we can still check to see, does the reconstruction I produce, is it consistent with these fields? So this is work that I, along with Chris Byrol, worked on, and we were actually able to basically run a hydrosim that's constrained to look like our real universe. And if you look at the specific, trying to compare this simulation to our own universe, here are the positions of actual galaxies with the dark matters and gas structure that the simulation finds. And although it's not perfect, because the kind of quality of data we had and the selection affects the galaxies, we're still able to get quite a good match between the simulated large-scale environment and the galaxies. So here's another cute video showing a fly-through of our constrained what we call Cosmos TNG volume, a hydrosim of what is roughly the real universe. So we can extend this effort various ways. So we can do a joint analysis of doing both galaxies and Lyman-Alpha forest. PFS will be targeting both of these in the volume that we're observing. And we can see a lot of kind of demonstrations of synergistic reconstruction, where the Lyman-Alpha forest is probing the large wavelength modes quite well. The galaxies are highly biased. They're really picking out the centers of the overdensities. And so if you look as a function of scale, the joint reconstruction is better than either the galaxies only or the Lyman-Alpha forest only would do individually. You can look at this again in terms of cosmic web. We get really great cosmic web reconstructions from this type of joint technique. And so we can use these reconstructing maps for a lot of interesting science. So Benjamin Zhang, who was a student at UC Berkeley and worked with me and KG Lee to do efforts of intrinsic alignment. So essentially seeing if you have a galaxy that's near a cosmic structure, how much does its spin axis align or anti-align with the direction of the cosmic structure. And so we looked at this in terms of this deformation tensor approach, and to actually see would PFS-like data combined with HST or HSC-like imaging, would we be able to pick out the signal? And so this is quite model dependent, of course, because if there's no intrinsic alignment in the universe, you're not going to find a sign of intrinsic alignment. But if we kind of assume a certain model for intrinsic alignment, here based on this Horizon AGN simulation, we found that we were able to both reconstruct the alignment signal at redshift 2 and at redshift 1. So redshift 2 from Lyman-Alpha forest and redshift 1 from a galaxy population. We can go dive deeper into galaxy reconstructions with this method. So this is work led by Zhenze Dong. It's currently ongoing. Hopefully it'll be on the archive in the next couple days. And the idea here was that we wanted to really make a super realistic galaxy model and see how well could this TARDIS-like reconstruction approach recover the cosmic structure. So here we used a semi-analytic model for the galaxy formation, used a dark matter, popular dark matter simulation, and added in all the selection effects, and did it on the full light cone. So really trying to throw all the bells and whistles in terms of what types of instrumental effects could affect the reconstruction. And still we were able to get quite good large-scale structure reconstructions in this volume. Further going into cosmic web, we were able to get very good cosmic web reconstructions as well. So we're hoping to use this technique for PFS for the galaxy populations. So now the kind of cool thing going forward is we want to push these types of techniques to smaller scales. So there's a lot of assumptions that are baked in when we're doing a bias model expansion. And kind of philosophically, what the bias model is doing is it's throwing away all of our prior information about galaxy formation. Right? We're just assuming galaxies are some bias tracer of the underlying dark matter field. But as everybody who works on galaxies knows, there's a lot more complicated physics going on with their evolution. And just given a dark matter field, there's not a one-to-one correspondence with the dark matter field and the galaxy field. So a similar thing is true with the gas, right? As we saw the fluctuating Peterson approximation, it works pretty well at big scales, but at small scales and in dense environments, we see a similar kind of deviation. And so if we're able to better model this in our forward simulations, we can perform a similar kind of field level reconstruction and constrain the gas properties. So the goal here was to take our favorite hydrodynamical equations, the Euler equations. These are the equations that basically control things like shocks and fluid instabilities that we see in a lot of cosmic environments. To code up the solutions of these equations in JAX, so we can use these automatic differentiation tools. We can deploy a lot of this optimization framework. This was all kind of inspired by the Athena code, if anybody here has played around with Athena. So really try to keep the numerics as accurate as possible. So there's not necessarily any neural network augmentation, no major approximations done. We really want, at the level of the numerical precision, to match these kind of benchmark codes. And that way, when we do these reconstructions, we get the initial conditions. If you don't trust my code, you can still go in and plug it into Athena, or you can plug it into your favorite hydrodynamical simulation. And then it's less of an issue of, is the optimization finding the right thing? It's more an issue of, are the numerics of the simulation dominating? And so you can play the same games of reconstructing whatever field you want. So this was a reconstruction I did. This was now a year ago. I think I made this for an earlier talk in Taiwan. So the code parallelized across 4 GPUs, and this type of optimization only took, I think it took roughly an hour to do. So full hydrodynamical evolution for this turbulent field to make Taiwan. So you can add in gravity to these things too. So here's an example where I started an initial Gaussian random field and figured out the phases such that in projection, kind of analogous to the earlier Taiwan map, in projection it looks like dihydro, the name of the code. So again, in these examples, we're back propagating through and able to update the initial phases to perform this kind of reconstruction. So kind of the philosophy is, if you can forward model it, you should make it so that you can reconstruct it too. So here's now the more complete example, adding in dark matter, adding in co-moving coordinates, doing this with UV background fluctuations and heating, cooling, kind of all the baseline physical models that most hydrodynamical codes agree on. We're able to evolve these kinds of boxes down to low redshift in a, not quite a blink of a second, but something where I can go make a coffee, come back, and have it be done. And so here you can see the heating cooling rate, and we'll use this later on. The heating cooling rate ends up being important for making proxies for various observables that we'd be interested in actually observing in a real-life universe. So this is just the forward evolution. Now we can go in to actually use this differentiable framework we spent so much time developing to reconstruct actual gas observables. So going back to our lime apple forest, here we have some kind of toy example here, but still now we're doing full hydrodynamic evolution. We imagine we have some noisy map of the lime apple forest flux. We'll evolve our hydrodynamical simulation forward. We'll use kind of a real pipeline for how you get lime apple forest from the simulation, modeling the neutral hydrogen, doing the line of sight integration as you would do for an actual spectra. And we can perform the same optimization. Again, you can see the initial conditions, the true density field, this is the observed flux. Within 90 or so iterations, we get a really good reconstruction of the underlying gas density. You can go into other observables too. I think this is kind of where the kind of main limitation is, where you really need to understand the instrumental properties to actually do this reconstruction, kind of the mapping to observables. So I'm quite interested in hearing what people have to say about their favorite observable and how to maybe get it into this type of framework. But here is an example kind of my understanding of X-ray emission, which is that X-ray emission is proportional to the cooling rates. Maybe true, maybe some other technicalities there. You can imagine we have some X-ray-like observable here. And we want to reconstruct to find what types of cosmic structures would correspond to this type of map. So here again, we're doing the same kind of iterations, and we're able to reconstruct in this case, I don't show the initial conditions, just the late-time gas density, late-time gas pressure, and what we would infer as our actual observable. Here's another example, still with X-ray, just with a kind of denser cluster. This one actually, for whatever reason, converged much faster to a reasonable solution, so we don't have to wait even that long to get for these really massive clusters, to get a quite nice reconstruction of the underlying density field and underlying evolution. So now we want to add in subgrid physics. So this is because, again, we know that simulations, you're not going to capture across all cosmic time or all cosmic scale. There's going to be these processes that are happening on time scales shorter than you really want your time steps of your simulation to be, as well as on scales much smaller than you would be able to realistically evolve at the same time as you're evolving the cosmic web. And so what we do in these cases is we have various analytical approximations or kind of our best guess of what star formation is doing. And this is kind of the secret sauce of a lot of these different hydrodynamical simulations. You can go to various workshops and conferences where people argue for quite a while about which subgrid physics is better for modeling which physical processes. And I think the kind of future of the field is really trying to figure out what is a flexible parameterization such that you can actually fit all of different observables all at the same time, which is what I think a lot of this differentiable hydrodynamical, this type of approach could get at. So here we're going to kind of have a really simple toy model, kind of as like a supernova feedback stellar formation model. The idea is that if we have a pixel that's below a certain temperature, so this is some cold gas, and above a certain density, so cold dense gas, you're likely to form a star with some given probability. And then, for the purpose of this simulation, I'm just letting the stars release all their energy at once. So you can, of course, extend this various ways, let the stars evolve further, or continually inject energy, or change metallicity rates, but for the time being, we're just going to let them inject energy all at once. And so this is pretty easy to code up in terms of the forward model, but you do have to be careful with how you backpropagate through this. Because we're doing something stochastic, you really have to start looking into the machine learning literature to figure out how do you backpropagate through these kinds of stochastic processes. This is a topic that comes up a lot in machine learning because when you have a car driving down the road, and you have a self-driving car driving down the road and you want to train it to react to the environment, there are a lot of processes that are essentially stochastic, right? Maybe a person pops out in front of the car, maybe a person doesn't pop out in front of the car. You're driving down a road and you either have to make a left or a right. Which one do you choose? So it's very both discrete and possibly very random. So we can use a lot of those techniques. I used them earlier in an earlier paper to just do galaxy population modeling, but here we can actually use them for subgrid physics as we run the simulation. So here's kind of a forward example of simulation. This was actually earlier, I made this earlier on in the simulations you saw early, so it's not quite as pretty. But we have an example there where we have some dark matter collapse in form structure, you have gas collapsing, you have energy injection, and you can kind of see the stellar mass evolving with it.
So what's the scale?
The scale, so this is, I think this is I want to say 25 MPC box.
Oh. I thought you want to go to much smaller scales to test the subgrid modeling.
So this is not so much testing the subgrid modeling in terms of like this whole physical chain, right? So for this physical chain, obviously we need to, if you really want to model this exactly, you have to, do crazy high resolution or kind of multi-scale different box simulation. Right now, what we're trying to do here is we're saying, given a given subgrid physics prescription, can you fit the parameters to the data? And the idea being that you could come up with really broad subgrid physics prescriptions in abstract and fit those to the data rapidly. So you don't have to spend, billions of CPU or GPU hours running a big grid of simulations to explore the parameter space. You just kind of quickly optimize to figure out what the best fit parameters are. So this one here is kind of meant to mimic the forward simulation as you would see it in a standard hydrodynamical simulation. This is a little bit more restrictive because we're doing a Cartesian grid, and it's not quite the full illustrious TNG combined type of evolution. But
to get some idea, so for particular case, how many hyperparameters do we have?
So in terms of the, you're saying in terms of like the physical parameters, or?
Yeah. For example, I think you're fixing maybe cosmological parameters, but many parameters.
I'll actually give you, let me show it to you in this next couple slides that actually do a fit for some of these parameters. So in terms of what overall happens, because you're injecting energy, kind of the main things people in the field talk about is this small scale suppression of power, suppression of power at small scales, where as you increase feedback, you essentially push down the matter power spectrum. So this is an observable that people have been kind of getting at with weak lensing signal particularly, but you can kind of talk about in terms of TSZ and some other probes as well. And so the idea is that we see the same kind of qualitative behavior with this toy model, where as we turn up this energy injection scale, So basically injecting more and more energy with our subwave physics parameters, we suppress the power. In this case, due to various numerical effects, it doesn't quite go quite as low as you saw in those plots. Those plots are more correspond up here. But we can still do the same kind of fits and actually try to fit, given a matter power spectra, can you fit parameters to it using the gradient information. So this is doing this HMC sampling. So we're not just trying to find the best fit power spectra, we're trying to find the full posterior of those fits. So in this particular case, all I did was fit 4 parameters just for demonstration. So 2 cosmological parameters and 2 astrophysical parameters. This is kind of a self-consistency check because I made the data with my own code and I'm checking it with my own code. So certainly there'll be more steps necessary to fully validate it against other codes and actually then apply it to real data. But one of the key things here is that as we increase the number of parameters, the rate of convergence doesn't slow down that much. It's when you're already calculating gradients, it doesn't cost very much to calculate another gradient. So you basically get the full vector of gradients out of it. So you can do really large parameter spaces. So people who've done kind of bias model approaches for cosmology before, they were doing fits of omega matter, sigma 8, plus all the phases too. So here I kind of randomly sampled the phases rather than trying to fit them. You can actually fit the field plus the parameters all at once in abstract.
So, are you able to recover the input from the?
Yeah, sorry, the input parameters are this green dot here. So our posterior samples, whatever you want to say, is consistent with our input cosmology. And input astrophysics too. So kind of going into this direction of applying these types of techniques to PFS, already with diff hydro, we're already kind of nearing the right scale. So this is just actually my latest box. So this is these benchmark illustrious TNG simulations that a lot of people here have probably worked with. Just kind of showing they did a grid of simulations of different sizes just for comparison. And so while a PFS pointing is kind of this size, or this is I think the XMM field here. So that's of order 300 megaparsecs. Our current latest diff hydro runs are like 50 megaparsecs. So with just a little bit of work, it's not such a big leap of scale to do a single PFS pointing and maybe with a bit more HPC effort do the full volume. And already these ones are quite fast. So I can do a reconstruction of this size box within the order of a couple hours. So certainly once one goes to a full HPC setup, it is not so unusable to actually reproduce the full PFS field. So in the final, I guess, few minutes, I want to talk about going to even smaller scales. So already we're kind of looking at IGM size physics. Can we actually use the same techniques and apply it to ISM physics? So one of the things here that really motivates me, at least when I was a little kid, I love looking at old Hubble pictures or nowadays JWST pictures of these supernova remnants and nebula. So basically the physics here is there's a big a dying star that goes supernova, injects lots of energy, injects lots of momentum. That energy injection, momentum injection, end up interacting with the ISM, heating and cooling ends up causing these what's called like a thin shell instability to form. And you get these kind of fluid instability-like features on the border of your remnant. So people have simulated these kinds of things. This is the Athena K code showing the forward modeling of it, and they didn't do any particular work to try and make it match this famous one, Cassiopeia A. It looks maybe similar. You can kind of argue about whether or not it is or is not actually matching. But of course, if we're able to put this all into a differentiable framework, we could actually try to run a simulation that exactly matches this remnant. So this is a very highly nonlinear problem, but we can still try to make the code work in these types of cases. So here's just kind of an example showing a couple of these supernova remnants. Here's just one diff hydro forward run when I was trying to test the code. Again, the kind of concept is if you can forward model it, you can try to reconstruct it. So you want the code to work in the forward model. You want to be able to debug whatever numerical artifacts are going on. And the goal here would be to do a reconstruction of one of these supernova remnants and be able to then try to pick apart a lot of the uncertain physics of both the initial supernova explosion as well as possibly the turbulent driving forces in the ISM. And so this is a field that I don't know very much about the ISM or these types of processes beyond what I've been looking at here. And so it'd be very cool to interact with some people at ASIAA who know more about these types of physics. And so here was an example. I was actually first trying to reconstruct Cassiopeia A, or not reconstruct, but forward model Cassiopeia A. So I got all these little nodules on my remnant. I was like, oh, this item actually looks like Tycho A, but just pretty picture level. This was kind of a nice example of deploying dihydro at scale. So we were actually able to parallelize dihydro across 16 GPUs and do 1024 cubed. This is actually kind of getting into a real HPC-like domain. And so if you're able to do the same kinds of things with the cosmological reconstructions, you're already getting at that PFS field like volume. So the idea for our forward simulation is we initialize velocity perturbations to basically source the turbulent ISM. You let that run for a bit to basically let these phases mix. You then inject a small blob of energy and momentum at the very center of the box. This is the supernova, and you let the simulation run and let this remnant form. And the goal will be to backpropagate through to find initial phases. I was hoping to have the Cassiopeia A one done by now, but I said I only have my test problem. So here's an example where we generated a fake supernova remnant. So this is the projection. Here is the actual targets. This is what the underlying simulation was for our remnant. You can kind of see visually it looks kind of similar to this one, but we weren't specifically trying to match it. And here I initialized the phases randomly for the ISM, and we were able to iterate through. And within 30 iterations, we're actually able to get a quite good match to the simulated data and the simulated target. So again, this is running forward 30 supernova reconstruction, or 30 forward modeled supernovas in a really large parameter space. But in the end, it only took, I think this one took 10 hours. So I had it run, I went to sleep, I woke up the next day, and you got your pretty supernova remnants. So maybe I'll skip over this for the sake of time, right? Because we end at 20 after, is that right? I'll just kind of end with kind of my vision for the future of going into this and how I think these techniques will go forward. And I'm very excited to, of course, now that we've developed all these techniques, apply them to actual PFS data. So there's a lot of, currently a little bit of waiting for PFS because there's still ongoing reduction efforts. But we're really kind of gearing up for deploying these types of techniques to do joint optimization, to be able to constrain this environment galaxy connection. From the simulation framework, there's of course a lot of work to be done in adding in more physics to these types of simulations. I think fortunately a lot of this work is actually getting easier and easier with ChatGPT's help, and people have been playing out agents. I've been having a lot of fun playing out agents for helping to basically debug the code, write it down. A certain cooling module doesn't quite work. I have ChatGPT look at the actual C++ code that's there in Athena, compare it to my code, and so that's quite a good job of figuring that out already. But the goal will be, of course, to add in additional fields. So we'll be adding in magnetic fields, adding in chemistry, adding in radiative transfer, make this as realistic as possible. This is also a great opportunity to add in neural network type augmentations. Because everything's differentiable, you can train not just your initial conditions, you can train neural network corrections in loop with the model. And so that gives you kind of a really controlled way to switch off between rapid convergence that maybe neural network augmentation will enable you to have, basically speed up your simulation a lot, or numerical precision of really solving out all the equations and keeping that physics as accurate as possible. So you have kind of a knob there you can turn. Then, of course, the real power of these types of techniques is folding in as many observations as possible. So I'm currently working on trying to add in better instrumental models, so going beyond just saying X-ray equals cooling, but actually try to model the specific systematics of X-ray observations, or model specific observations of radio observations within this type of framework. And I think kind of going to the broader, in terms of like the 2 to 5 year time scale, I think these types of approaches can really push across the scales. So one thing that I was showing here was using kind of simple grid-like simulations, where you kind of evolve the hydrodynamical fields on a Cartesian mesh. A lot of modern codes, like the illustrious simulation, use smooth particle hydrodynamics, where evolving gas as a particle. So I've been working a lot on kind of the tree-based algorithms for that. But in the end, a lot of it will come down to computing power. Right? If we want to reconstruct the universe, we need to start deploying these things on these exascale systems and really utilize a lot of kind of these big supercomputing clusters, things that people in the US have been building to do this kind of modeling. So I think deploying these types of frameworks there will be really powerful. And I think with these types of approaches, we can start to get at these kind of underlying questions. What are the subgrid physics models that best represent our universe? How do we relate those subgrid physics models to the underlying small scale physics? And in particular, how do we most optimally combine all these observations to do this joint analysis? So with that, I'll leave up my conclusions and leave time for maybe a couple questions.
Thank you very much. I forgot to mention that Ben has been playing an important role in PFS, as he alluded to. He will also be leader of the vetting team for the PFS non-evolution target selection. So thank you very much for this exciting talk. Let's have questions.
Yeah. So about the dark matter simulations, if the goal was to reconstruct the initial conditions, wouldn't it be easier if you just run the simulation backward and treat gravity as a repulsive force?
So that does work in certain cases. So like the gravitational dynamics for something like particle mesh code is formally reversible, right? So you can actually, if you know all the particles' positions and velocities, you can run it backwards. But the issue is in terms of these, what we observe is the gas density, and and that might be really incomplete. So you might have holes in it, you might have really noisy properties. So it's not like we can actually observe those individual particles to be able to reverse them back. So at the simulation level, sure, if you actually are given the simulation of the particle catalog, you can reverse it. But the actual likely comparison is on the data level. So we have this very lossy compression, essentially, you can imagine it, of going from the dark matter particles to the observed fields. And because we're given the observed fields, that step is reversible. So you're left with the idea of forward modeling it, doing the likely comparison, and then going back through. And so in terms of the gradient calculations, those are fine. If it's lossy, it doesn't matter. That's what neural networks do, right? Where you have a complicated, many-layered convolutional network, and at the end it tells you, yes, cat, yes, dog, or something like that. So you can still backpropagate through that. But
yeah, I'm curious to know your kind of scientific directions for the PFS galaxy evolution effort. Yeah. So would you like to focus more on the reconstructing the underlying fields, the dark matter gas, using the PFS data, or would you like to actually include like more physical fundamental parameters, like for example, dark matter self-interacting cross-section, or maybe biasing parameters or feedback model to constrain these kind of physical parameters as a hyperparameters? Which one would be more feasible for the PFS?
well, I think certainly in terms of just feasibility, like immediate feasibility, the first thing, just like reconstructing the dark matter density field, is less technically demanding. So like in that case, you can do these things where you run the dark matter simulation, you assume a bias model, you paint on your line map forest, you paint on your galaxies. Maybe you can do something slightly fancier with how you do that. But that certainly is, quote unquote easy. Like the pipelines for that I've already built and already tested on hydrodynamical simulations, and they're well it's ready to go, given the data. The other thing I think is much more exciting. I'd love to be the person who discovers self-interacting dark matter, or something like that. Would certainly be the childhood dream of discovering new physics. But you know, there's obviously some technical implementations that are required, and a lot of domain level expertise. Kind of the way I see it is I'm building up this framework, but the real kind of next steps is people who have a particular science base. So if somebody comes to me who loves simulating self-interacting dark matter and has that domain expertise, we can try to figure out the right way to interact those two things. That's kind of how I view the specific kind of extensions beyond that. Like, so for example, with Ken Nagamine at Osaka, he's quite interested in kind of AGN feedback and supernova feedback at high redshift and how that interacts with the IGN. So I'm working with him to include those kinds of models in DiffHydro so that we can do that kind of joint constraints. But personally, me, I'm like, AGN, big black hole, something cool happens, okay. But, you know, requires that domain expertise, I think.
So I'm curious, so you use supernova remnant as an example to get into small scales. What do you think of planet formation?
Yeah, that certainly would be very cool to do. I know even less about planet formation than I do about supernova remnants. Like, well, one of the main difficulties of, like, you know, one thing I have thought a bit about is like globular clusters, where you have lots and lots of individual stars all interacting. When you really get into those kind of chaotic dynamics, it gets quite hard to do this really explicit inverse modeling, just because, not so much because you can't backpropagate through it, just because it's so sensitive to the noise in the data that it becomes numerically unstable. There probably are cool additional approaches for that. And so I imagine something similar would be true for if you really want to model like an exoplanet forming, doing this whole thing. But again, there's probably some interesting applications. We can look at summary statistics of various sorts and possibly apply the same kinds of approaches there. That would be my hope, at least.
Can you go back one slide?
Sure.
CMB, you mentioned, that's the definite initial condition of our universe.
Yeah.
And the current universe is the definite current condition.
Mm-hmm.
And can you really?
Yeah. Well, so I guess when I wrote that down in English, I said CMB anisotropies or secondary anisotropies. So doing things like TSZ and lensing. So there are some works with this kind of, so the kind of overarching theme of this, some people would group as hierarchical Bayesian modeling, where you kind of have parameters you care about. So those would be maybe like the density field. Parameters you don't care about, maybe like the actual primary CMB. And so people have set up the same kind of problem where you have a high dimensional inference task using gradients to do, for example, CMB delensing. And for that kind of case, you're jointly fitting the CMB with the lenses along the line of sight. And in the end, maybe you don't care about the CMB, or maybe you don't care about the dark matter along the line of sight. You kind of have choices in how you set it up, depending on what physics you care about. So there could very well be a case where you're actually given the CMB map, and one of the outputs would be the actual delensed CMB example.
I see.
Yeah. So, again, you kind of have choices of how many approximations you want to make. Certainly kind of the ultimate goal would be you just give me the data streams of every single observation I pop out the universe. But there's certainly lots of steps before that kind of thing. I think I'll probably be retired by the time we get to there.
Okay. One final question.
So you said that like to reconstruct or to find the initial condition in a very short amount of time. Is that because the simulation itself is very short amount of time?
What was that? Sorry. Oh,
I said you said you only need like several minutes to find the initial condition in some cases. Is that because the simulation itself is a short amount of time?
Yeah, I think the dominant thing there is that the simulation itself is really fast. So that comes from this GPU acceleration. So this isn't something that like only I have worked on. A lot of people work on GPU accelerated codes for these types of tasks. But I think getting a lot of the like a lot of these other kind of techniques, for example, like tree-based methods, things that people haven't yet thought about putting together on GPU. I've been working on putting on GPU, and it really accelerates the actual forward simulation. And then the main other thing is how you set up the problem to try and minimize the number of iterations. So there are a lot of techniques you can do to try to speed up the convergence of it. So for the TARDIS method, I did something called annealing, or a kind of multi-grid method, you could call it, where basically at first I reconstruct the largest scales, and then I reconstruct the smaller scales. And that makes the code require way fewer iterations to get to a converged solution. So there are techniques like that. You can also do things, for example, with the full hydro, right? You could do something, a hybrid, where you first run TARDIS to reconstruct the what you think is the dark matter distribution, and then you start that full hydro with that as like an early state. And that way you don't have to run the full hydro 200 times, maybe you'll have to run the full hydro 10 times to like refine the simulation. So there's a lot of games you can play to speed up things.
So this is what you did with Cosmos TNG.
So with Cosmos TNG, that's a bit different in that we didn't iterate on Cosmos TNG. That was just one shot because that was full, like I was with this repo code, all on CPU, no gradients. Took a very long time to run because basically the idea there was we were running something that was, I think it was roughly equivalent to TNG 100 or TNG 300, but with those additional conditions. So it took, I don't know the exact wall clock time, but order weeks to run one simulation. So we just called it at one. But the goal would be, yeah, to do this thing iteratively.
So before we thank Ben for this talk, I just wanted to note that we have reserved like half an hour, maybe, for non-faculty members to interact with Ben. So after we thank him, so faculty members will leave, and you guys can talk to him with whatever topics you have in mind.
Tell me all the exciting gossip.
Yeah, so that's thank Ben again.